What? Wait, what do you mean about that? There's more geometry?
No, I said you're right about that.
Oh, okay.
Now we're going into algebra 2.
I like algebra too, it's pretty fun.
Quadratic functions and factoring. I figure we're going to have time for about 2 chapters, is what I think. And I mentioned matrices, but I am actually going to shy away from that. Let's put up the prerequisite skills. Yeah, let's take this down a little bit.
Can you post this on Schoology?
The lesson, yeah. Actually, I posted the homework and I forgot. I was going to post the lesson. Let me do that now. Try to stand off to the side so you can see the screen. I need a folder called Zoom Lessons. I'm going to make a folder right now. Add folder. There's a new folder called Zoom Homework. Now this one's going to be called Zoom Lessons. Zoom Lessons. Copy. Okay, that's period 1. Zoom Lessons. Let's go ahead and copy to courses. 4, 5, and 6. Okay, so now everybody has a folder called Zoom Lessons. Now I have to go down, get that lesson. I'm going to download it. There it is.
For the homework, are you going to say at the end that we don't have to do all of it because
It's going to be evens.
Okay, so it's the whole thing from 2 to 51, 2 to 54, 54?
Even. Yeah.
Okay.
Wait a minute. Here we go. Algebra 2, lesson 4.1. I'm starting in chapter 4 of my Algebra 2 book, my particular book. Save. There we go. It's almost time to begin, but that's okay. I want to put this in there for you guys. You could have it out in front of you. You guys can get it right now as soon as I put it in there. Okay, so now I can upload that file. Zoom Lessons. Let's go in there. And let's upload that file. Here we go. It's coming soon. You guys will be able to open it up and go along with me here. Algebra 2, lesson 4.1. There it is. Okay, so I'm uploading it, so it's going to take a second. And then I'm going to I start in period 1, and then I'll copy it over to everybody else. Oh my gosh, 30 messages? You guys, you messaging me on the weekend? All right, it's 8:30. Can you guys still see the screen of problems, the warm-up you should be doing?
I cannot see it.
What book is this from?
It's from an Algebra 2 book that I have.
Okay.
Okay, so it's in period 1. Now I'm going to copy that over to the rest of you. Copy to courses.
Can't really see the warm-up.
Okay.
Copy what?
The lesson.
Oh, I see.
I'm going to give you guys the lesson so you can see it. Zoom lessons. You guys have 2 new folders now. You have a Zoom lessons folder and a Zoom homework folder. The homework is going to be in there now. It's already there. I'm putting the lessons in there now. There you go. It's loading, 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 and everybody has the lesson. You can go ahead and open that up right now. I'm going to go back to this to make sure everybody can see what's up here. Can anybody see this now? Or no?
Can't really see it.
No?
No,
Okay.
only slightly.
Then what we'll do is we'll enlarge this. We want the X-intercept and the Y-intercept. Just kind of a review here.
We can't
This
see
got
the.
I know, it's not dragging the way I want it to drag for some reason. There we go. Okay, now
Oh,
can you
that's
see it?
easy.
Okay,
Yeah, it's easy.
so this is prerequisite knowledge going into this chapter. What's the Y-intercept here?
0, 2.
Going
0,
back
comma 2.
Well, prepare yourselves, folks. We're going back to algebra. Things are going to change. This is the first time you're going to get to see. You should be thinking along the way, how did that geometry course that we just finished, how does that affect the way I'm going to go forward in mathematics with algebra, with what used to feel familiar to you as the algebra? Now you've been away from it so long. Okay, so now we're coming back to it and we're thinking, well, what are some questions I should ask along the way is, why does this work? Because in algebra, a lot of the times, they're not going to tell you why stuff works. You'll have to investigate. All right, you'll have to ask questions. I don't know why a lot of stuff works. I mean, I can get answers right, and I know how I can make them work for me and get the answers right, but not everything I know why it happens. So maybe we can learn some things together here. Okay, so the Y-intercept, the X-intercept, right? So the X-intercept is 3, 0. The Y-intercept is 0, 2. Okay, let's go ahead and drag this. I don't think you guys need to review if you just substitute a -3, but it's checking to see if you know your order of operations. So I guess we can skip that. If you plug in can you guys see this now? Is it big enough?
Oh, yeah, I do.
X equals -3. You plug that in. What we don't want is students to multiply it by -5 first. You want to square it first, get 9, and then get -45.
Now it's
and
really
then
blurry.
-44. Okay, I think you guys know about absolute value. This is what we need you to know. These are the prerequisite things that you need to know. And I select the hand and it still doesn't want to grab it.
Ah, that's a problem.
What does the absolute value graph look like again?
A V.
That's a good question. So if you have to think
It's
about
a,
you have to think
it's a
about,
V, yeah.
let's talk about that. Okay, the basic absolute value one without any transformation is that. Now there's different ways to transform that. You can transform it up, down, left, right. You can make it, you can horizontally squeeze it or vertically stretch it, or you can vertically squeeze it and horizontally stretch it. So there's all sorts of, what was that?
Nothing, sir.
You can also make a negative.
So if you want to investigate how to do all those different things to it, then what you would want to do is you'd want to go into Desmos and use the sliders. Right? So I guess you can say that the equation is y equals a, and then in here you have x minus h, where have we seen that before, plus k. And this is just a is 1. There's other stuff, I mean, because then I could put like a b right here. That's going to affect it if I put a b inside versus outside, because on the outside it's going to get distributed. Well, no, I don't want to do that. I don't want to do that. Here's what I want to do. I want you to see that the A is a little bit different than the B because the B only multiplies to the X. The A gets distributed and changes both of these. So you might want to put a slider here in Desmos as well to see what that does. When that's less than 1, when that's more than 1, when that's what's different when that's less than 1 and more than 1. What happens is you slide these and you investigate the difference of what happens to the graph. But if you just want to start with the original one, when X is 0, the absolute value is 0, so you get 0, 0. When X is 1, Y is 1. When X is 2, Y is 2. So you just get basically Y equals X on the right-hand side.
When X is -1, Y is 1.
So where the graph would have come down this way, you'll see that when you take the absolute value, when X is -1, you're going to come back up again. So it's going to be a reflection of this line over the Y-axis. We're talking geometry talk, right? So every point here is a reflection of a counterpart over here. This has a counterpart, right? They're reflections of each other. They're the same distance, and the segment that connects them is perpendicular to the line of symmetry here, the reflection line, which is the Y-axis.
Oh, by the way, Mr. Rostal, on a slightly unrelated topic, I did research Kramer's rule, and apparently someone did find a pretty intuitive proof of it, and they cited their sources. There are actually 5 different proofs on Math Exchange.
Oh, fantastic. Is there
I
any way
also,
can you send me a link so that I could share it with everybody?
yes, I think I also know how to use it now.
Great. And you know what's unfortunate about that is that we're not going to do matrices. I decided over the weekend that where I wanted to focus. I wanted to focus in, and it's not because, you know, it's not for simple reasons, but the main reason is because I found some exciting things in there that I thought were fun and were very useful for you to have on your tool belt going into Algebra 2. So I'll talk more about that as we go along. Okay, so here you see 7, 8, and 9 are transforming. So what happens when you add a 2 out here? All it does is it takes this one and it bumps it up 2.
Oh, Mr. Rostal, one last interruption. I'll send the link by Schoology. I'll just paste it in as a URL and send it by Schoology's message.
Okay, great, thank you. What happens when you subtract 3 in here? Where is this vertex here? What is the Y value? The Y value is 0.
0.
If I were to slide this right or left, what would the Y value be?
0.
0.
It would still be 0. So if you think, what would X now have to be to make the Y value 0? It wouldn't be -3, would it? What would X have to be here to keep the Y value on the X-axis?
3.
It would have to be 3. So this actually doesn't slide it to the left 3. You need a +3 to make Y 0. So 3, 0 is actually the new location of the vertex. So subtracting 3 in here slides it the opposite of the sign. It slides it to the right. Because of that you're trying to slide that point. You're transforming it. Once you slide that, then all points along the graph, they slide along that same vector pathway in the same direction, the same magnitude. See, I can talk geometry talk now because you guys have that. Without that course, it's a little bit different, the explanation. Okay, gives you a different perspective. Any questions about that? All right, what happens? Please let me drag this. I want to drag this. It won't let me drag it. I wonder what's different about this now. It's because it's part of the picture. So maybe I need to click outside the picture. Not letting me drag it. Okay. So what I can do is I can shrink it. Nope, shrink it. And I want to grab this, and it's not letting me grab it. It's not cooperating. So I guess I can do this, but then you guys can't see it very well, right? Is that right? You can't see it very well?
I can't see it very well.
Yeah. And then if I zoom in, then it's not letting me drag this over.
And everyone should open up the slide on their home computer because it's available on Schoology now, so you can just use that instead of having
Yeah.
to.
It's true, but when you select the hand up here, it should not go back to the arrow.
Is there a slider down at the bottom that you can use?
Oh, there is. Thank you. I was just finding that as you were saying that. Thank you.
Maybe
Right.
if you use a hotkey.
There we go. We got it. Okay. Let's look at this case here. I want to deselect it so it's not blue. There we go. All right. So let's take a look out here. What does that do? Now you've gone back and you're not sliding it from the vertex, but what you're doing is you're making this negative so that when this becomes positive, then the negative is multiplied to it. So that negative is going to flip the V upside down. The 2 is going to make the slope twice as steep. So it's going to do this. It's going to close in. It's going to go down 2 over 1 instead of down 1 over 1. Okay, so it's going to
Wait, Mr. Ostal, negative 2 times absolute value of x on Desmos produces a downwards absolute value curve.
That's what I said. It's going to flip the V upside down.
Oh yeah, yeah, and it's I think it gets vertically squeezed in comparison
And I
to
said
a
that
negative.
too.
Oh.
Yeah. Well, I didn't say the words vertically squeezed. I said the slope would get steeper. The slope would have been like that. It would have been that. But so if I would have just flipped it upside down and just put a negative here, it would have made these dotted ones. Actually, those would have gone the opposite direction as the pink ones. They would have been opposite rays. And here would have been an opposite ray to the pink one. But what it did is, okay, so you're calling that a vertical squeeze. We have to check on that language because there is a difference between a horizontal stretch and a vertical squeeze. They're different things. And you will learn those next year. But I think I don't need to go over the terminology because I don't know it yet. I think it's important, though, for you to know what it's doing and just visually see what it's doing. Because you're going to do this again in Algebra 2 in just, in a few months from now. You're going to be doing this anyway. All right, so I just want you to see what it's actually doing. All right, so by putting a 2 out there, now what would happen if you put the 2 inside the negative 2? What would happen? What if you had this?
That would be the same thing, wouldn't it? Except positive.
Just plug in values. When x is 0, y is 0. When x is 1, then you get negative 2, and then you get 2. So you're going to get this. When x is negative, negative 1 times negative 2 is 2, and the absolute value is 2, so negative 1, 2. So if it's in there, it does that. So it did affect the slope. Okay. What about number 10? What does this -5 do? This is the horizontal slider here. In order to keep the vertex where it is on y value of 0, x would have to be, if you didn't have a 4 here, x would have to be +5. So that's going to bump it over to +5. But then the +4 is going to bump it up 4. So you're going to have your v over here. That's what it's going to do. And it's just a transformation. It's a translation. It's just a slide of the v up here. To the right 5, up 4. But what I want to investigate is this. What is this going to do? What would that do?
Well, we know that the x plus 1 would shift it horizontally, and the
What
2 would squeeze
direction?
it. It would shift it to, well, it would shift it to the left, wouldn't it? Because the negative 1 shifted it to the right.
Okay. This would shift it to the left because, forget the 2 now. How would you get it back? So how would you keep the y value 0? X would have to be negative.
Yeah,
So
and the 2.
So the vertex being on the y value of 0 has to slide left in order to, so you have to make x -1 to keep the value 0. So you slide it to the left, okay? And then what does this do? Well, go ahead and plug in some values now. So start with your vertex is at -1. -1 plus 1 is 0. That's why 0 times 2 is 0. So you're there, okay? And then try, what happens at x is 0? What happens one space to the right of that? 0 plus 1 is 1. 1 times 2 is 2. Ah, look at the slope. It's up 2 over 1. It affected the slope. Okay? And then what about if I go x is -2? -2 plus 1 is -1. The absolute value is 1. 1 times 2 is 2. It's just a mirror image. So it made it steeper and it bumped it over. So it can be seen here that, oh, this translated it to the left one. This doubled the slope. Even though it's going to do this, right? It still just does those two things is all it does. So it didn't matter that it distributes. So then my question is, what happens when you get just that? What's the difference between the two? It should be different, right?
It isn't in this case. Not really.
It is different.
Oh yeah.
How do you get the y to stay 0? It's something different. It's not, this affected the horizontal movement. Having the 2 inside affects the horizontal movement. Doesn't it? Underneath my hand must be -1 to get a 0.
2 outside?
The
2 outside is steeper and moves it over.
Hold on. That's what it means. Okay, so the 2x here has to be equal to -1 to make a y value of 0. So that we want to see the vertex shift. Okay? All right, so then
-1/2.
if x is -1/2, y is 0. You're on the x, you have found the x-intercept. Okay, so let's see.
So is that the vertex?
Yeah, that's the vertex. So we're playing a game of chase the vertex, follow the vertex. Where did it go? Well, it slid to the left, -1/2. What happened? Putting something inside there, it divides. You divide the amount of horizontal shift by that. Okay, and you can see why. We went through the motions of it. So that would make the vertex here, but the slope would still be up 2 over 1. Up 2 over 1. Up 2 over. Look at the blue one and look at the orange one. They're essentially the same steepness. So the 2 in both of these cases affects the steepness of the same way, but it affected having the 2 inside affects the amount, the magnitude of your horizontal translation. Out here, it does not. What's funny is my first thought when I was deciding what curriculum to do was to do this in the last chapter, and then to take something from this chapter and something, and I thought, well, that's not going to be as cohesive because then I can't just give you a chapter with a review, a quiz, and all that stuff. So I decided not to, so I was going to leave this out. And then for the prerequisite, we ended up doing it anyway, and it's actually going to gel much nicer this way. Instead of doing a whole section on this, now we got it. What's so important about what we're doing now and why I'm taking the time to do it is because this transformation affects everything. Remember what we did with circles. Remember how we horizontally translated the circle was with the x minus h. And then with the y minus k, we can move it up and down, right? It's very similar, and you want to see, and with all the objects, it's going to be very similar throughout all the objects we work with. We're going to be getting into parabolas and moving those around, okay? So what we're going to do is we want you to make the connection back to this absolute value, how we're translating it. It works with lines. It's just harder to see with lines, because with lines, it's hard to tell whether you moved it to the right or you moved it up, because I can get the same line, I can get the same effect moving something to the right as I do moving it up or down. Okay, right and left, I can get the same effect. I'll show you what I mean. If I start with some line like that, and I want to, I'm thinking I want to move it. Is that blue line moved up from the green line, or is it moved to the left of the green line? Get the green line onto, how do you move the green line onto the blue line? By moving it up or by moving it to the left?
Both.
Either. I could translate this up by adjusting the y in point slope form, right? So I have y minus k is equal to the slope times x minus h. Remember that was y minus y1 and x minus x1?
Yeah.
Point slope form. It's all the same. It's the transformation. I can adjust the k to move the green line up. And what happens is if this point moves up to that point, then all the points move up the same way. And if these are parallel, then no problem. This will rigid motion, right? It will all slide and map onto the other one by just moving every point up the same amount so that they're all on the blue line. But what I could have done is taken a point and moved it horizontally that way by adjusting the h. So what happens is when a teacher shows this to the students, they get confused on how the translation is actually working. Is it going up or is it going to the left? You can justify it either way. And now
Unless you have labeled points.
The what?
Unless you have labeled points.
Okay. But anyway, this is where Mr. Knaus does a ton of transformation all year long. He's going to do it with graphing sine of y equals sine of x. You get the sine waves and the cosine waves and the tangent graphs and all the cotangent and the, all the inverse ones and all of that. That's where you're going with all this. All right. And then he's going to transform them. He's going to move them. And some of his quizzes and tests are, can you get the starting one to land on this by manipulating the equation? And if you can you probably did that last year with him.
Mr. Rosenthal, how are you going to test us on these? Do these count? Are these going to count
Here's a
towards our
test.
grade?
Yeah, there's a test. All right. Let's see. What is down here? What is it? The directions here. Oh, solve the equation. Those
That's
are just
easy.
single variable equations. Okay, perfect. All right, now we can move on. Let's talk about what we're going to be doing this chapter. Looks like there's 10 sections. Quadratic functions and factoring, which is about where you left off in algebra, I'm guessing. At the end of the year, you've delved deeply into quadratics. So what I came up with over the weekend is that we should probably pick up where you left off and add a couple new things, right? Get that solid and then take you to the next level. And then the year will end and you guys will be all set to go into Algebra 2. All right, so matrices, they were really cool things that tie into linear algebra. You guys know what linear algebra is?
I believe so.
Yeah, I do.
After you're done with all your calculus, at the university, you finish all your calculus, you decide to be a math or engineering major, and then they say, okay, you got to take linear algebra now, right? And then you delve into large systems of equations that are with elementary algebra skills aren't enough. So then what we do is we learn matrices to learn how to solve these. And then all of a sudden, you know, they have all these implications, you know, all these, you know, real world problems that you can solve with the matrices. I was doing investigation. I saw a link to physics where they have cross products to get areas. And instead of doing the calculus, it could be solved with linear algebra with matrices instead. Because using the using the determinant, which is what some of you, if you looked over that over the weekend, I asked you to look at that. If you plug coordinates in and then set them up in a matrix and use the determinant, you are able to find the area of objects with certain formulas with that. So there's all sorts of interesting things. I decided not to delve into that. You'll have plenty of time to do that. I'm going to take you guys into the quadratics, all right? And then the quadratics will lead you right up until you're ready to do conic sections, which are the hyperbolas and the ellipses. If we have time, if we happen to zoom through this stuff, no pun intended, because we're on Zoom, then we'll do it. But let's just see where it takes us. Okay, so the first thing we're going to do is, do we remember how to graph quadratic functions?
Let's see another sign. Desmos takes arctangent, arccosine, and arcsine. And arcsecant.
Oh, thank you. Okay, so 4-1, we're going to graph quadratic functions today. Tomorrow, we're going to graph quadratic functions in a different form that you might not be used to, although I'm not surprised if Mr. Knaus taught you parabolas in vertex form or intercept form.
I believe he did the former.
Solving quadratics by factoring. That's with the coefficient of x squared being 1. Then it's solving where the coefficient of x squared is a non-1 number, where a is not 1. Solving quadratic equations by finding square roots. We're going to do complex numbers, imaginary.
Yay!
Yes.
Rob, no.
We're now going to complete the square with a different goal in mind. We're going to complete the square to get the quadratic into vertex form. Why vertex? Vertex form is the equivalent of point slope. Now you see a point. What's the purpose of point slope?
To get the line
Line.
that goes through a point with a certain slope.
No, to see all of this in terms of translation, moving them around different locations. All right, so the vertex form is so that we can translate the parabolas to new locations. We can move them up, we can move them down, we can move them right. You can steepen them, you can flatten them, squeeze them, stretch them. You can do all that. So vertex form, we're going to get there by completing the square to manipulate our equation to look like vertex form. Once you see it in vertex form, you can clearly see how the original one was translated and then place it on the graph. Okay? The discriminant, use the quadratic formula and the discriminant, graph and solve quadratic inequalities, and then write quadratic functions and models. So that I think that one's going to be to solve problems. So if we do our job here, this is what we're really gearing towards 410. How well do you understand it? If you understand it well, then when we get to 410, you will be applying it to real stuff, right? Which would be really cool if we can achieve that. So this is a tall order. I haven't really taught this in a class. I know the material. It's not super difficult. You don't have proofs to do. But what I need you to do is when you're confused about something, you need to ask. You need to stop the lesson and ask about it. Oh, I have some messages here. I wasn't here during a Friday chapter test. Aren't we supposed to make it up today? No, that's a rumor that we're making up anything. We're not making up anything. No makeups. It's just going to go as incomplete. You're not going to lose credit. Remember, in these times, I'm not removing credit from you guys. I'm just not going to give you credit towards trying to raise a grade. Okay? All right, let's go to the next slide here. Boom. All right, this is going to be a little bit large here, so I'm going to have to shrink this down. Hopefully everybody found the lesson now, and you can.
Yes.
If not everybody, but it's helpful because you might not be able to see this stuff. I use Cam Scanner to get all this material. Okay. And let me pull this over. Some words you should know: quadratic function, parabola, vertex, axis of symmetry, minimum value, maximum value. Okay, here we go. Quadratic function is a function that can be written in standard form, and I'll write it out for you. Okay, where a is not 0. If a was 0, it would eliminate the x squared term. So then it wouldn't be a quadratic anymore. So we want to make sure a is not 0. All right, c is a constant. A, B, and C are constants. They're just numbers. Okay, x and y represent points on a plane, not in space, in a plane. They're just different xy coordinates. Now, because there's two variables, there's an infinite amount of solutions for this, all right, which means that there are an infinite amount of points along this parabola. Let's say here's an example of one. These x, this x is the same as that x, and that y represents different points along this graph. Okay, and what a parabola is, and I already read ahead, they don't define it this way. They just say that it's a characteristic. But you could define a parabola as a locus of points in a plane that are equidistant from a point and a line. So if I have a point here and I have a line here, this line is going to be called the directrix, and this is going to be called the focus. Those are the two that I'm talking about in my definition of a parabola. So the definition again of a parabola, now in this book, they just talk about it as a characteristic, but I call it a definition. It's a locus of points in a plane that are equidistant from a point called the focus and a line called the directrix. So if this is directly underneath here, which is where the vertex will be, this is called the vertex. You need to familiarize with these terms, okay? This distance here, call that P, is the same as this distance here, perpendicular to that line. This distance is a point to a point. It's just straight, a straight, okay? But from a point to a line here, it has to be a perpendicular segment. So you don't see any perpendicular here, any marking, but you have to see it when it hits the line, okay? Now, how would that look like here? That would mean that all these points, by the way, this is not drawn to scale. Maybe I can fix that. If I want to know where the next point would have to be, it has to be somewhere that when I draw out to it, that distance is the same that way. That looks like I went a little bit too far. Let me fix that. I'm going to try to get it a little bit, maybe there. Okay. That means that it's looking like this.
What chapter is this?
Chapter 4 of the book that I'm using.
Okay.
Okay, so this distance here is the same as that distance there. Okay,
So what's the
this
definition
distance
of
here
direct?
is the same as that distance there. These are both the same distance here. All right. Any point along here, remember it's a locus of points, and that's how we finished. What is a locus? It's a set of rules for all your x and y's. Every one of these is an xy. The focus is not an xy. What would the focus be?
HK.
It would be an HK. All right. There's some equation of this line that's y is equal to something, right? Because it's a horizontal line. If parabolas are turned on its side, then it's x equals something and your directrix is a vertical line. Okay, so that's what we're getting into. All right, parent function. That's kind of what I'm talking about. The parent function is that one that has no translation done to it. You have a coordinate plane, okay? F of x, which is your y, is equal to x squared. That's your parent function. It is in this form. A is 1, B is 0, C is 0, which is allowed. You can have B and C be 0. Having B and C be something else is going to translate your parabola. Having A be something else other than 1 is going to stretch or squeeze your parabola. Okay? Or flip it upside down if A is negative, right? But before you do any translation, you're just going to get this, where the vertex is 0. The focus is somewhere up here, right? Which you could find out where that is. Okay, but the focus is somewhere up here. And the directrix is somewhere here, where this distance is the same as that distance. Okay, this is the same as that. That's the parent. Now, as we start to mess with this, it's going to move it around, okay? The y-axis in this is the axis of symmetry because all the points here are reflections of the points on the other side. A point here is a reflection of the point over here. Okay, so this is an axis of symmetry, right? It divides the parabola into two equal parts. Okay, so the parent function for the family of all quadratic functions is this. The graph of it is the parabola shown below here. Okay. If here, can you guys see this up here? To make it a little bit bigger.
Kind of.
Now?
It's a bit bright.
When x is 0, 0 squared is 0, so 0, 0. When x is 1, 1 squared is 1, so you get 1, 1. When x is 2, 2 squared is 4, so now all of a sudden you don't have 2, 2, you have 2, 4. When x is negative 1 and you square it, you get positive 1. When x is negative 2 and you square it, you still get positive 4, so it does what the absolute value one does. Except because you have an exponent, it's going to grow exponentially, so it won't be linear like the absolute value one. It will curve upward and get
The absolute value one more.
deeper exponentially. Okay? Any questions about this? Okay, let me take this back down to where I had it, 175. All right.
This is an example of positive feedback.
All right, so now I want you guys to graph this one. And I'll write it up on the board. So I want you guys to graph this one now and take a minute to do it. 2x squared. And then compare it with y equals x squared. So it looks like we're going to start messing around with the transformations. We might need to get on Desmos just to show the different. But it's good to do it without Desmos first, so you guys actually can lay them in. Ooh, actually, what I want to do, I want my quadrant 1 and 2 to be accentuated. Okay, and I'm going to do the red one first while you guys are working on it. Make a t-table. Okay, I like this. -2, -1, 0, 1, and 2. Why did I pick 0 in the middle? Because it has not undergone any horizontal translation. So I know 0 is going to be the middle point. Okay?
0 is a rock.
-2 squared is 4. -1 squared is 1. And then these are going to be reflections. So if this has a y value of 1, so does it on the other side. So I really only have to find out these, and then when I get to the middle of my parabola, the other side has the same y values. Okay, so I have this, 1, 1, 2, 4. Negative 1, 1, negative 2, 4. Come to say good morning to everybody. Oh, thanks for the water. Thanks, babe.
Good morning.
Good morning.
Hi there.
Thanks, babe.
A child.
Child. All right. Now I'm going to graph this one. And I'm going to do negative 2, negative 1, 0, 1, and 2. Negative 2 squared is 4. 4 times 2 is 8. Watch what I do here. Now I know that positive 2 is 8. Only because I know that 0 is the center. X equals 0 is a vertical line. I know that x equals 0 is my axis of symmetry. That vertical line, which is the y-axis. This is the y-axis. That's the axis of symmetry. How do I know? Because this has not been horizontally transformed, which we haven't seen yet, but you'll see it. You guys could probably put together what it looks like when you do that. Okay, negative 1 squared is 1. 1 times 2 is 2. So this is 2. And 0 is 0. So here we go. 0, 0. Negative 1, 2. Ah, look at that. It made it steeper. Negative 2, 8. 1, 2, 2, 8. There's something about doing it yourself versus just plugging it in and sliding it on Desmos that is a little bit more intimate. It's a little bit, I think it's better in a way. Or let me not say better. It's different, and you should probably get both experiences. So I recommend that if you really want to learn this and understand it, go into Desmos and play around with, you know, these transformations. Any questions so far? You could be the two who? What? Wait a minute. Host only. Darn. See, you guys got me for a while. Now only I can see your messages. All right, any questions about this? Hello.
No, none.
Okay, good. This should be a fairly a review.
I have a couple questions going, equations going on Desmos with parabolas.
Yeah, if you want, that's a great idea. Is if you have Desmos up and running, that would be great. There's the solution, which we saw. So you guys can see that here. They made a table. They made it horizontal. And then they have the two side by side here. Okay, it's just steeper is all that it did. All right, so when you adjust this is what constant was this called in standard form? That's the A, right?
A.
Yeah, so when A changes, you can either make it flatter or steeper.
One upside down.
You can make it upside down. Okay, let's try this next form. And again, if you have this lesson out in front of you, then you're on page 5 right now. I'm on page 5, then you don't have to wait for me to write it, you can see it. I wonder what you think that +3 is going to do. And you're going to compare this, of course, to...
the C,
You're going to compare this to the parent
oh
function.
yeah, that's what the C does.
That's the parent function.
Wait, in any parabola, in any equation where y equals x, but something happens to it, anything anything that's just a number will increase y or decrease y. Act directly on y because it doesn't have anything acting on it.
Please say that again.
Any number that's by itself, just plus or minus, will directly affect y
Exactly.
because there's nothing acting on it.
Check this out. Subtract 3 on both sides. What does that look like? It's translating the y by whatever that number is. So this is going to bump it up 3. Adding 3 on the end directly affects the y. It's a slider. It's a vertical slider. Adding 3 on the end, adding a constant on the end is just a vertical slider. Okay. Let's go ahead and do our parent one. 0, 0, 1, 1, 2, 4. Negative 1, 1. Negative 2 squared is 4.
It
Okay,
moves it up.
red is the parent. Now, you can try to predict what's going to happen here. This should bump it up. This being negative should flip it upside down. And the 1/2 should widen it. Okay, it should widen it. So let's see what happens with our x's and y's. Okay. Let's go. I can do 1, but I can do, I don't want it to get too large. So let me just do -2, -1, 0, 1, and 2 again. Okay, so -2 squared is 4. Okay, -1/2 of 4 is -2. Oh, and then plus 3. -2 plus 3 is 1. So -2, 1. Okay, and then 2, 1, right? Because it's going to be the same on both sides. -1 squared is 1. And then you get 1 times -1/2 is -1/2. -1/2 plus 3 is 2.5. Okay, so you get that. So you get -1, 2.5. You get +1, 2.5. And then at 0, what happens? 0 squared is 0. 0 times this is 0. 0 plus 3 is 3. So you can see what happened at x is 0. It's still in the middle. The middle did not get slid to the left or to the right. The middle didn't slide left or right, but it did move up because it's not 0, 0 anymore. It's now 0 and up here at 3. Okay. Wonder what would happen here at -3. -3 would be 9, and then we'd have -4.5. And then you'd have -1.5. So -3, -1.5. +3, -1.5. Okay? You can see what happened. It's not as tight. It's stretched out. Okay, it's horizontally stretched out. Okay? And flipped upside down because of the negative, and the vertex was bumped up. Questions about that? All right, we're easing our way in here, nothing too bad. If you look at this, this is ax squared plus a c. That's what happened. There's no bx term here, or you could say there is, and b is 0. Let's see what we have next. Okay, that's just they're showing it. We already got it. Okay, let's throw some more on here. Let's do these.
-4x squared.
Okay, well, let's not graph this. What is this going to do? Put it in the chat. Number 1, what is -4x squared? What is that going to do? Put that into the chat. Write it in there. Let me see what you come up with. I feel like some people are only going to include partial information. It is not going to move the vertex up. They did not add or subtract.
There you go.
You would have to add a constant out here. Flips it, and 4 times steeper. Flip it, 4 times steeper. Flip it and make it steeper. Makes it flip, not by, but making it flip over is only one of the 2 things that it does.
And 4 times steeper.
The vertex would not be upside down. The whole graph would be upside down. The vertex is a single point, so a point doesn't know what upside down is.
The upside down circle.
Right? And I'm not naming names, so you know who I'm talking to. Okay, so the vertex is not upside down. The graph turns upside down. Nobody else is going to respond? Okay, let's move to the second one. What happens to the parent function when you get negative x squared minus 5? Now tell me in the chat what's happening and I'll watch.
The everyone chat or PM?
It's 4 times higher.
What's 4 times higher?
Well, the graph is each point is 4 times the y value.
You're
Also
talking about
flip
number 1? Are you talking about number 1?
Yes.
Number 1, it gets steeper and flips
Yes.
upside down. But we're
Yeah.
on number 2. We're on number 2.
Oh.
Okay, and you're putting it in the chat.
What is it?
It's negative x squared
Minus 5?
minus 5. Yeah, can you see it? Oh, I just pushed the board down a little bit. Okay, so y equals negative x squared minus 5. I want you to tell me in words what it's going to do. Instead of graphing it, I know you guys can make t-tables probably just fine. Just tell me in words, what does it do to the graph? How does it transform the graph? Put it in writing, and I'm going to start reading them. Parabola moves down. That's only part of what happens. Makes it flip and 4 units higher. Oh, that's the last one. Flip upside down and moves the vertex down 5. Keep going. Type what you think. Moves down 5 and flips. Yeah. This flips upside down. Right there. This translates parabola down 5 units. Okay, good. And then this last one, a 4th x squared is going to flatten the slope, right? Of increase. And plus 2 is going to move it, shift it up. It's going to translate
Yeah,
it.
the vertex goes up.
Okay. Okay, I did practice for there. Moving along. Okay, let's see what this says. This says properties of the graph of the standard equation. Okay, let's look at the properties. And let's make them big, and we'll look at one at a time. Can you guys see them, or should I make it a little bigger? Let's make it 250. There we go. Can you see that? Yes or no? Can you see this? I want you to see this. Can you see x equals negative b over 2a?
Yeah.
No, not really. I mean, I see it now because you mentioned it, but before I couldn't even see what it was.
300. How about now?
That's better.
Better?
But wait, in any y equals ax squared plus bx plus c, x equals negative ba over 2a?
Yes. Okay. So I'm going to introduce you guys to a concept here. This is a calculus concept. Now, we're not going to prove it until you get to calculus. But when you have now you have some tools to understand it. If I have a graph of a parabola, what would it mean to have a tangent line? What would be a line?
Oh, it only touches the vertex.
That's only in, what about tangent there? What would a tangent line be at that point?
It would be the slope. It would be the slope of
Touches it
the
in
function
one
at that
point.
point, wouldn't it?
Hold on, I'm not asking that. I'm saying, what would it mean to have a tangent line to this parabola?
Go through it.
This would be secant, wouldn't it?
Yeah.
That's
You-
a secant.
You could do the vertical line that's in the diagram. That would never touch it, except at that point.
So a tangent line would be a line that touches at that point and only at that point.
It would have to be vertical.
No?
Or like that.
Okay. But as this steepens, what about at that point? Would the tangent line have the same slope at a different point?
No.
No? You're right, it wouldn't. It would be steeper up there. And as you get closer here, what's going to happen to the slope of that tangent line?
Well, at the vertex, the slope is going to be 0.
Wait, let's not go to the vertex yet.
Yeah, the limit.
What about there? What's happening to the slope of my line?
Lower slope, lower slope, lower slope.
Decreasing.
It's decreasing, it's flattening.
As you reach the limit.
As you get to the vertex, it's a horizontal line, it's 0.
Yeah.
Then if you come up this other side, it goes negative, right? So the derivative in calculus,
Oh, so that's why if you set the derivative to be 0, you can find the local minimum of a function.
correct. The slope of the tangent line to a function.
The derivative is
The
the
derivative.
slope of the tangent line,
That's what the derivative is.
but the slope is changing.
But yeah, but the derivative doesn't change.
At a point, at a given x. At a given x, so you would plug in the x. So let's take a look at that.
Oh yeah, derivative of x squared is 2x, right?
So there is a proof, this is called the exponent rule for derivatives, is that when you have a situation with a variable, let's say like that. What is the derivative? It's the slope. What is slope? Right?
Mhm.
Change in y over change in x, right? All right. So delta y over delta x. What ends up happening when you find delta y with respect to delta x, what ends up happening is this. You get this.
Wouldn't it be a time? Well, it would be a times nx to the power of n minus 1, right? Oh,
That's it. So
that's the power rule, I believe, Mr. Rosenthal, not the exponent rule.
power, yes. Okay, so the delta there, I'm going to call it d, dy. That one, delta, is a triangle in the Greek alphabet, so delta d, dx.
Are you
That's-
using Leibniz notation, Mr. Rosenthal?
No, well, I don't know, I've heard the name, but I don't, that maybe. Okay, so delta y over delta x is slope. See it? That's slope. And that's what it's equal to. So you have to take this and multiply it to that. And then the exponent is 1 less than what it was. Now, let's see how that works.
So for x cubed, it would be 3x squared, right?
Watch this. What is this that I have here? What is
The
it?
quadratic equation.
It's the standard form, right?
Yeah, standard form for parabola.
Okay. What's the exponent on the x here?
1.
1. Okay. Where's
Well,
the x here? Can I put an x here and
Oh,
say
0,
x to the 0?
which is equal to 1.
All right, hold on. So that is a parabola. Right now it's a parabola. The slope of a tangent line would be dy dx, which we know is defined by each one of these. You have to do that rule. So there's your n. So this one will be 2 times a.
2a
This is
x,
x to the 2 minus 1,
which is 1.
1.
And the other one would be b.
Hold on.
Because
This is the n for this term. That's this n is 1 times b is b.
And then plus 0.
X 1 minus 1 is 0. Plus, check this one out. 0,
0.
0
Yeah,
times c is 0 times x to the 0 minus 1.
to the negative 1 power, it's still 0.
So that 0 is gone. So now we learned something, that when you take the derivative, the constants are eliminated.
yeah.
Okay, and that's equal to this is equal to dy dx. This
Wait,
is,
that's the slope of a tangent line at any given point.
this at any given point. So how do I know which point I'm at? By setting the x equal to a point you want to see where the slope is at that point. So if this is this parabola is representing the motion of a projectile, and you want to know what the velocity of it was at a frozen point in time,
Yeah, that's the main application.
what you're doing is you're finding the slope, the rate of change. Isn't velocity the rate of change
At that point.
of distance at that point in time? Right? At that point in time, how fast was it going at that moment? Right? So then x, if x is measuring time, you say, well, how fast was it going 1 second after I dropped it or after I launched it? Then you would plug x1 here, right? By the way, let's simplify this. This is just 2ax
Plus b.
plus b times, what is x to the 0 power?
1.
It's 1,
Yeah,
so
one.
this is b.
So you do get a new constant, which is
Hold on 1 second. What is the slope at the minimum point?
0.
0.
By the way, the minimum point is the vertex, always. The
The
vertex
slope-
is the minimum, or it could be the maximum. And what we know is that a tangent line has to be, watch my hand, has to flatten out to 0.
As it approaches the
means,
limit.
oh, wait, please, wait. So the slope I can substitute here is 0 at that minimum point. Now, solve for x.
And then to find out whether it's a minimum or a maximum.
Hold on. Solve for x. Subtract b on both sides.
Negative b over 2a.
Divide by 2a on both sides. X is equal to negative b over 2a. Where, David? Remember we're saying, well, where? It changes, right? Where did this occur? When the slope of the tangent line was 0, which it could only be at a minimum or a maximum. Now, somebody mentioned, how do you know if it's a minimum or a maximum from here?
Second derivative test.
If a, well, you could, but if you already know what, if you have an actual problem, if a is positive, you have a parabola that looks like that, the parent parabola. Then you know it's a minimum. If a is negative, then it's flipped upside down and you're finding a maximum.
Well, that's in the case of a parabola, but in the case of other functions, you could just
Correct.
use the second derivative test, where if it's positive, I think it would be minimum, and if it's negative, it's a maximum.
Well, we're not going to go there right now, okay? Because I want to keep it here. All right. So negative b over 2a is equal to x at the vertex. That means if I translated this over 1,000,000 units to the right, and you're trying to do a t-table, you're not going to find it. So it's useful to know where to start. I want to find where the minimum is if it's out at 1 billion, okay, or up at 1,000,000, or if it's translated somewhere far away. I want to know where it went so that I can graph the rest of it. I want to graph these and their mirror images. I want to graph that and its mirror image. But I got to start at some central point, the vertex. So it's useful if x is equal to negative b over 2a always at the vertex. Once I know what that is, I can plug it back in to find out what my y coordinate is. So once I know what this is, I can plug in my x is whatever this value is in for x, and guess what? When I solve it, I will have what y is at that coordinate as well. Okay, so that's a good stopping point. There won't be any, you can start the homework if you want, but we definitely want to come in tomorrow and look at the other properties. All right, so you guys are dismissed. Have a wonderful day.
Mr. Rosenthal.
The office hours begin now.
Bye.
I have a question. So I submitted my chapter 12 test. I think it was like 3 or 4 minutes before the deadline, and it said that I never submitted it or anything like that.
Okay.
And I'm not sure exactly if I maybe submitted it in the wrong folder or something. And I think I remember there being like a chapter 12 test. Like,
some people said that they submitted it to the instructions.
yeah, I think I may have accidentally
have
submitted
no
it to the
idea what that-
instructions.
How do you even do that?
I'm not
Because
sure.
the instructions are an assignment, yeah.
Oh, okay. So the
It's supposed to
instructions
be
are an
an
assignment, And does the assignment show, the instructions, did they show up as an ungraded assignment? And is it in the, okay, so maybe I can find it in there.
Okay, if I did and it's not able to be found, is there any way I can resubmit it?
Well, hold on. Let me see if I can find it right now.
Okay, because I still have the files and everything and the pictures.
Let me look and see if it's in the grade book, that instruction assignment.
Because I think I accidentally submitted it in the instructions as well.
And that might be totally fine. But when I look here,
I don't see it under grids.
I see an assignment for chapter 12 test in the grid. I do not see an assignment here for the,
So I still have the pictures of my test that I sent. And
I just don't know
submitted.
where would I find it, you know?
I'm not sure. If you'd like, I can
You
resubmit
might
it.
want to try this. Go to materials, go to Zoom test, and click chapter 12 test instructions.
They're not there anymore. I got rid of those.
Oh. Did you delete the assignment? Maybe?
I deleted it from the materials folder.
You
And you're
probably
not the only one. There were several students that submitted it there.
Okay, so
those submissions
maybe-
are probably lost and you have to resubmit them.
okay, I still have the pictures of my test. If you'd like to, if you'd like, I can resubmit it.
Just who am I talking? Who am I speaking with?
Shy.
Shy, go ahead and submit them, please.
Okay, and do you want me to submit them to chapter 12 test or somewhere else?